Okay, testing. Okay, my name is Victor. I'm from the Hong Kong University of Science and Technology, and the title of my paper is Distant Oracle on the Terrain Surface. And my collaborators are Raymond Wang, Chen Long, and David Mount. So here is the outline of my presentation. I will first give the introduction, including related works. And then I will present my proposed oracle, and next I will present my experiment. And finally, I conclude my paper. So first, what is a digital terrain surface? So the digital terrain surface consists of vertices, edges, and faces. So consider this example. So every black point is a vertex, and every edge connects to different vertices. And every face has 3 adjacent vertices and 3 adjacent edges. And in this example, there were 2 points of interest on the terrain surface, S and T. So there were 2 paths between S, T. One is EP, and the other one is GP. EP is the shortest path between S and T in the Euclidean space, and GP is the shortest path between ST on the terrain surface. And the length of GP is called the geodesic distance between S and T. Okay, next, let me introduce some notations and concepts. Let V denote the set of vertices on the terrain surface, and let P denote a set of point interest on the terrain surface. And let big N denote the cardinality of V, and let small n denote the cardinality of P. And let DG, ST denote the geodesic distance between S and T. So consider this example, and there were 17 vertices. In other words, 17 black points. And there were 2 point interests. So in this example, big N is equal to 17, and small n is equal to 2. And the DG, ST is equal to the length of GP, okay? And this geodesic distance queries have many applications. Let me elaborate one by one. So in the first application is a geographical information system, GIS in short. It has many landmarks and residential sites of animals. And the geodesic distance between the landmarks measures travel time and travel cost between the landmarks. And the life scientists study the migration patterns of animals by using the geodesic distance between the residential sites of animals. And the second application is computer graphics and vision. So in this application, each 3D model has some reference points. In other words, point of interest. And the geodesic distance between the reference points capture the features of a 3D model. And the geodesic distance-based feature is used to measure the similarity between 2 3D models. And the third application is the scientific data 3D modeling. And scientists usually model their studied objects, such as organs, with 3D models. And there are many reference points on the 3D model, which corresponds to the functional units. And the geodesic distance between the reference points usually is used to make analysis together with the MRI images. So the first application is a 3D location-based virtual game. Let me take Ingress as an example. And this game has many portals, and each portal has a location. And the users travel from one portal to another to play the game. And the geodesic distance between the portals is used to measure the travel time and the travel cost between the portals. And the last application is spatial data mining. And in this application, it's very important to measure the inter-cluster distance and the inter-class distances. And in the mountainous area, the geodesic distance will be a good metric. Okay, although there are many existing works on computing the geodesic distance, they are not efficient enough. Let me categorize them into 2 categories. The first category contains the algorithm for computing the geodesic distances on the fly. So there are 3 exact algorithms, and the best one takes big O, big N, log big N square time. And there were 2 approximate algorithms. They obtain better efficiency with accuracy as a trade-off. And but they are still not efficient enough because both of them takes big O, big N, log big N running time. And the second category is a distant oracle. And as far as I'm concerned, there's no exact distant oracle on the terrain surface. And among all the approximate distant oracles, the state-of-the-art provides optional approximate distances. And the major idea is to introduce a large amount of standard points on the terrain surface and standard edges, okay? and transform the terrain surface into a very large graph and index the graph. And so it's called SP oracle. And due to the large amount of standard points and standard edges introduced, it has a large space and a very large building time. Besides, this oracle is not POI aware. So in the example that I showed before, there were only two POIs, S and T. So storing a single distance is enough, but this SP oracle still introduces a large amount of standard points and standard edges, which is cumbersome. And there are algorithms for other queries such as KN and reverse KN, but they are irrelevant to our problem. So let me summarize my contributions. We studied three types of distance queries on the terrain surface. The first one is POI to POI query, P2P in short, where POIs are known a priori. The second one is vertex to vertex distance query, V2V in short, where each POI is located at a vertex. And third one is arbitrary point to arbitrary point query, A to A in short, and POIs are not known as a priori. So in this presentation, I focus on P2P only for the sake of the limited time. And in this paper, we propose a distance oracle SE, and it has the accuracy guarantee. Specifically, it provides optional approximate distances, and it significantly outperforms the state-of-the-art by orders of magnitude. So the major idea is that SE indexes the approximate pairwise distances between POIs directly, and this avoids the introduction of the large amount of standard points and standard edges. So let me compare the state-of-the-art SP oracle with our oracle in theory. So we consider two cases. Case one is that small n is less than big N. And one thing I want to show is that small n is typically than big N in practice. So for example, in the Eagle Peak data set, small n is equal to 4K and big N is equal to 1.4 million. And in the Bear Head data set, small n is equal to 4K and big N is equal to 1.4 million. There are two benchmarks used in the literature. And so in this table, we use big O tide notation. And this notation ignores the log factor and the optional for better clarity. And this table shows building time, oracle size, and query time. And compare with SP oracle, our oracle has a comparable building time, smaller oracle size, and a smaller query time. Here, H is a very small constant, and it is smaller than 60, even in an extreme case. And in our experiment, we show that H is always smaller than 30. Okay, then the next case is small n is larger than or equal to big N. So in this presentation, we don't show this case, but we could also handle this case. And our oracle still outperformed SP oracle. In this case, in both theory and practice, the result is omitted here for the sake of limited time. Okay, let me present our oracle next. Our oracle contains two components. Component one is a compressed partition tree. It indexes all POIs and each node corresponds to a disk. And the second component is a node pair set. It contains a set of node pairs, and each node is from the compressed partition tree. And each node pair is associated with a distance. Okay, in the query phase, we need to build the compressed partition tree. And to construct the compressed partition tree, we first build a structure called partition tree. So let me introduce a concept called disk. So in this example, there were 11 point inches on the terrain surface, P1 to P11. And there are 6 disks. So let's first consider the red disk. It centers at P7, and its radius is equal to R0. And R0 is equal to the geodesic distance between P7 and P11, since P11 is on the boundary of the red disk. Okay, and we denote the red disk by D, P7, R0. And then let's consider the blue disk. And the blue disk centers at P2. And its radius is equal to R1. So R1 is equal to half of R0. And we denote the disk by D, P2, R1, okay? Then let's see an example of the partition tree. So each partition tree has a center, and we list the center of each node just next to the label of the node. And each node has a radius, and the nodes in the same layer have the same radius. So the radius of layer 0 is R0. The radius of layer 1 is R1, and so on and so forth. And R1 is equal to half of R0, and R2 is equal to half of R1, and R3 is equal to half of R2. Okay, and based on the center and the radius of a node, we could find the corresponding disk of the node. Let's say, for example, O21, the red node. Its center is P7, its radius is R0, and its corresponding disk is the red disk, and which centers at P7 and whose radius is R0. And then let's consider the node O18, and its center is P2, and its radius is R1. So the corresponding disk of O18 is the blue disk P2 R1. Okay. And note that the corresponding disk of each leaf node contains only one point of interest, which is its center. And each leaf node is called the corresponding leaf node of its center. So for example, the node O1 centers at P1. So O1 is called the corresponding leaf node of P1. And O2 centers at P2. So O2 is called the corresponding leaf node of P2. Okay. And we construct the partition tree layer by layer in a top-down order, and details are omitted here. Okay, then we transform the partition tree into the compressed partition tree. So we first find all the nodes in the partition tree with only one child. So in this case, there were two nodes with only one child, O18 and O17. And the parent of O18 is O21, and the child of O18 is O13. So we remove O18 and assign O21 to be the parent of O13. And for O17, the parent of O17 is O20, and its child is O12. So we remove O17 and assign O20 to be the parent of O12. And finally, we assign the radius of each leaf node to be 0. Okay, then we go to the second component, node pair set. And let me introduce a concept called containing first. So a node O contains a POIP if O is OP or an ancestor of OP, where OP is the corresponding leaf node of P. So let's consider this example. And so the corresponding leaf node of P1 is O1. So in this case, the node O13 contains P1, and the node O16 contains P10. And then let me show another. Let me continue this presentation. A node pair O prime contains a pair of POIs S and T if O contains S and O prime contains T. So in this example, a node pair O13 and O16 contains P1, P10. Okay. Okay, then let me present the node pair set. And we denote the node pair set by S, and each node pair in S is well separated. By well separated, we mean that the distance between the two nodes is larger than 4 over epsilon plus 4 times the maximum radius of the two nodes. And the distance between two nodes is defined to be the distance between their centers. And this means that their distance is very large compared with their radius. And each node so for any 2 point interest S and T, there is exactly one node pair O prime in S containing ST. And each node pair in S is associated with their geodesic distance, and details are omitted here. Okay, in the critical phase given 2 point interest S and T, we need to find the node pair O prime containing ST and return the geodesic distance between O and O prime as the final answer. So in this example, epsilon is equal to 2 and S is P1, T is P10. And we first find the path from O1 to the root and the path from O10 to the root. Okay, and then we find the node pair O13, O16 is a node pair in S containing ST. And so finally, the geodesic distance between O13 and O16 is returned as a final answer. And the distance is equal to dg P2 P10. So in this example, our estimation is dg P2 P10, and the real distance is dg P1 P10. So as could be observed from the figure, P1 P10, P1 P2 are close to each other, and P10 are far away from them. So from this observation, dg P1 P10 is very close to the dg P2 P10. And our estimation is equal to 10, and the real distance is equal to 9.6. And so the multiplicative error here is 0.042, which is much smaller than epsilon. And the only issue left is how to find the node pair OO prime in S containing ST. A naive method takes big O H square time, where H is the height of the compressed partition tree. And we also propose an efficient method which takes only a big O H time. So let me present the naive method first. So it tries all node pairs containing ST. So in this example, S is P1 and T is P10. So consider the path from O1 to the root and the path from O10 to the root. Okay, and then it finds a set AS containing all nodes on the path from O1 to O10, and it finds a set AT containing all nodes from O10 to the root, and then it makes Cartesian product of AS and AT. So in this graph, each edge it corresponds to a pair in the Cartesian product of AS and AT. So it's very dense. And in this example, there were 12 pairs considered, and it takes a big O H square time. Then we also propose an efficient method, and this method is based on an observation called layer property. So each node pair O prime in S satisfies a property called layer property. So we don't show the detail for the limited time, and it tries every possible node pair such that it contains ST and it satisfies layer property. So in this figure, in this graph, each edge corresponds to the node pair tried by the efficient method. And as could be observed, this graph is much sparser than the graph that I showed in the last page. And in this example, and there were totally 8 pairs considered. And this algorithm takes big OH time. Okay, next, let me show my experiment. And in the experiment, we used 3 real data sets, Bearhead, Eagle Peak, and San Francisco. And they have 1.4 million, 1.5 million, and 160K vertices respectively. And they have 4K, 51K point interest respectively, and the point interest are extracted from the OpenStreetMap. And we implement all the algorithm in C++, and we conducted its experiment in a Linux machine. And we consider 2 baselines. The first one is SP Oracle, and it's the best existing distance oracle. And we also consider the K algorithm, which is the fastest on-the-fly algorithm, and both of them provides epsilon approximate distances. And we adopted 3 measurements, oracle building time, oracle size, and query time. So this page shows the results on the San Francisco data sets on wiring epsilon. So as could be observed in each figure and in each measurement we adopted, our oracle SE outperforms the 2 baselines by orders of magnitudes. So finally, let me conclude my paper. We propose a distance oracle on the terrain surface. It returns epsilon approximate distance, and it significantly outperforms the state of art by orders of magnitudes. So thank you very much.
Have any question?
Thank you for the talk. In your introduction, you mentioned you considering 3 types: point to interest to point of interest and vertex to vertex, and you say that each point of interest is corresponding to 1 vertex. So what's the difference between these 2 as long as you have one-to-one mapping here?
Oh, okay. In general, a POI is located on any location. It may not necessarily located at vertex. So in the example in the very beginning, let me see. So in this example, there are 2 point interests, S and T. But S is not located at any vertex, and T is not located at any vertex. So POI may not necessarily locate at any vertex. And so the first case consider the general case, but the second case is a very vertex to vertex is a special case of the POI to POI query. Okay.
That's okay, I don't need them. So a question about the performance of your technique. So could you please go to the performance evaluations, maybe the last few slides. So I noticed your experiment platform has a 48 gigabit of memory.
Yeah.
So and your according to your evaluation, your data structure, your whole oracle fits in the memory.
Yeah.
So basically, you're assuming this is in memory. The tree you constructed is a memory data structure.
Yeah.
So have you considered like what is this performance on limited memory, on the machine with limited memory, like?
Oh yeah. This would be a very good research direction in the future, I think. So in this work, we only consider the memory-based algorithm. So I think it's very possible. For example, you use a mobile phone, so there is a very limited memory.
Yep.
So what we can do? So this is a very good research direction. So I will consider this in the future.
I think the good thing is, even if I want to use your oracle on the cell phone, I usually only care about a very small area where I am currently in. So I think that's okay. Yeah. But it would be nice to do some experiments on that. Thank you.
Thank you very much.